Hello everyone, let's study the geometry of a single camera. This is called camera calibration. So we want to see why we need to study this camera calibration and then look at the perspective projection model and then we look at the intrinsic camera parameters, extrinsic camera parameters, calibration and briefly about triangulation. Intrinsic parameters means the parameters that characterize a camera that are internal to the camera. Extrinsic camera parameters are the ones that are outside the camera, extrinsic to the camera. That means depending on how you have located the camera with respect to the world coordinate origin. So the main question that we have is, given an image, can we recover the 3D structure? So for example, in this case, this is just a single image, and using the geometry and the architectural information in the scene, they have been able to recover the 3D structure up to some extent. And you know that using deep learning techniques now, a single image 3D reconstruction is possible. So now how these images have been obtained? So for example, in this image must have been obtained by keeping the camera close to the pumpkin with small aperture so that the whole scene is in focus, so that these people who are far away are also in focus. Similarly here. So now let's look at the single view, so-called ambiguity. That means we are not sure, given the image small x, where the actual 3D point capital X that gave rise to this small x. So that capital X could have been there anywhere on this ray, right? So using the single view ambiguity, you can generate these kind of nice artworks also. You can see the image here. And then anamorphic perspective, these are things that are drawn and so on. So you can look at these links. Yes. Then here, this image, there is an image here, and that image is there. So you have to apply a transform to recover that. Okay. So our goal is to recover the 3D structure from images. So when certain assumptions hold, we can recover the structure from a single wave. In general, we need multiple waves to recover the 3D structure. But first, we need to understand the geometry of a single camera. So that's the motivation to understand the geometry of a single camera. Then we'll look at the perspective projection model, intrinsic camera parameters, and the extrinsic camera parameters. Okay, so let's look at the perspective projection model. So here you can see a normalized camera coordinate system. The camera center is at the origin. This is the camera center. The principal axis is the z-axis. It's called the principal axis or the optical axis. X and y axis of the image plane are parallel to the x and y axis of the world plane. So world plane capital Y, world plane capital X, these are parallel to the image axis small x and small y. So this is the image plane. So you can see there is this 3D scene signified by a capital letter capital X. There is a light ray going through that and striking the camera center, and you can notice that that ray cuts the image plane at small x, and that's the point where the image is made. So in the 3D scene we use capital X, and then in the imaging plane we use a small x. This is on the image. Okay. So now we can take a slice of this, including this y-axis, this slice, y is its slice, and then you can see the small x is right here, and the capital X is right here. So we signify capital X by x, y, z, and small x by x and y on the imaging plane. So this distance is the focal length, and this height, this distance to the object is capital Z, and the height of the object is capital Y. And using similar triangles, you can calculate this as Fy divided by Z. The reason is Um, as you know, if you consider this as small y, small y divided by capital Y is equal to small f divided by capital Z using similar triangles. Okay. So now if you want to write this in this fashion, a similar equation holds for small x also, and we want to write that in matrix form. So you can see we have written uh, this in this fashion. So you can see we take the first row and multiply x, y, z and 1. So you usually add a 1 to the end of these coordinates. So these are called homogeneous coordinates, and we don't have to worry about it right now, but just know that by adding 1 to the Cartesian coordinates you can get the homogeneous coordinates, and if you get something like this, the third coordinate is some number. To obtain the Cartesian coordinates you divide the two other coordinates, fx divided by z is actually the x coordinate, and y coordinate would be the second one, fy divided by z. So exactly this, right? So you can see with this representation you can obtain the effect of the perspective camera. So here this f multiplies y, and that's why you get fy, and here 1 multiplies z, that's why you get here. So this matrix, and we have not developed it fully, is called the camera projection matrix or the camera matrix. This is capital X, and this we term as small x. Yes, and this is the sign, let's say, millimeters, and capital X is also in millimeters, not in pixels yet. Small x is not in pixels yet, in millimeters. Okay, actually you can see small x is some scaling factor times x, y and 1. So this unknown scaling factor cannot be found right now. So we can then write this projection equation as lambda x equals px. So this equality is up to a scale, so therefore you can write it in this fashion also. Okay, so now let's consider the relationship between the camera's coordinate system and the world coordinate system. So assume that there's a rotation r and translation t. So therefore camera calibration, figuring out transformation of the world coordinate system to the image coordinate system. So this point 3D point is this 4 by 1 matrix, and world to camera coordinate transformation matrix would be r, t, 0 and 1. So actually this r is a 3 by 3 matrix. So r is a 3 by 3 matrix. So let me write this as 3r 3 by 3. Translation is in 3D, so therefore it's a 3 is also a 3 by 1 matrix. And then this 0 is 0 transpose. It's a 0 transpose is a 1 by 3 matrix, and 1 is a 1 by 1 matrix. Okay, it's a scalar. So therefore you can see this matrix that we have here is a 4 by 4 matrix. Then we have the so-called canonical projection matrix. It's I and 0. I is the I3, so I3 by I is a 3 by 3 matrix, and then the 0 is a 3 by 1 matrix. So therefore this matrix, as you can see, is a 3 by 4 matrix. And then in front there is a so-called camera calibration matrix, camera to pixel coordinates transformation. So it's millimeters to pixels matrix. It's called capital K, and it's a 3 by 3 matrix. And then the 2D point is a 3 by 1 matrix lambda x. Remember, we have to divide by the last coordinate to extract the Cartesian coordinates. So I hope this is clear. So this one is called the extrinsic camera parameters. They are extrinsic to the camera, right, depending on R and T, rotation and translation. And this is called intrinsic camera parameters. So intrinsic camera calibration matrix. This K includes the principal point, that means the center of the camera, scaling factors and the focal length and so Okay, so when you combine them, we have KRT. The formula for P, the camera matrix, is K times RT. Okay. So now let's incorporate the principal point, and slowly we will start incorporating different kinds of parameters. So in the normalized coordinate system, the origin of the image is at the principal point. So here is the origin. But we want to bring the origin to here or there, as we would usually represent images. So to do that, the image coordinate system, the origin is in a corner. So therefore, this is Px and Py with respect to the origin at a corner. This P is Px and Py. So therefore, small x must be this one plus Px, small y must be this one plus Py. So therefore, we can incorporate that into the equation like this, and therefore you can see here, in addition to f, you get Px and Py. Okay, so that's the principal point. Then when you have it decomposed, this capital K looks like this calibration matrix, and canonical projection matrix is this one. Okay. Yeah. So what are the units of the focal length f and principal point coordinates? And these are still in millimeters. What units do we want the measuring image coordinates to be? They must be in pixels. So therefore we need to introduce scaling factors from mapping from world to pixel units. And for that we must look at the CMOS or the CCD of the camera sensor. Now when you look at the camera sensor, there is it is composed of pixels, as you know. For example, you can have the resolution, so you can have 600 very small sensor times 800. So now digital cameras have 4000 by 6000, like that, large ones. So mx is a pixels per actually millimeter, we can say millimeter in horizontal direction. Mi is pixels per millimeter in the vertical direction. So the pixel size would be 1 over mx and 1 over my. Okay, yeah, so these in millimeters. Okay, so therefore now we have to have the scaling factors. So pixels per millimeter in horizontal direction mx. So when mx multiplies something in meters, so you know that you will get in millimeters the focal length. Yeah, so therefore you have alpha x, alpha y, beta x and beta y. So all these things are in pixels now. Okay, so this is called the calibration matrix in pixel units. Okay, in general, the camera coordinate frame would be related to the world coordinate frame by a rotation and a translation, as we saw before. So in homogeneous, non-homogeneous coordinates, that means we are not adding this last one. The transformation from the world to normalized camera coordinate frame is given by r times. This tilde symbol is used to signify non-homogeneous coordinates, r times x minus c. So coordinates of the point in the world frame. So if you take this point, it's in the world frame, but we want to get it to the camera frame. That's why we subtract c and multiply by the rotation matrix r. So c is this one. Okay, coordinates of the camera center in the world frame. Okay, 3D rotation matrix. Coordinates of the point in normalized camera frame. So once it is in the camera frame, we can multiply it by the camera matrix to obtain the coordinates of the image plane. Yeah, so this is what you get. Okay, so in non-homogeneous coordinates, x cam with respect to the camera r x plus t. So then in homogeneous coordinates, we can add 1 there, and therefore it looks like this. So now it's very nice in homogeneous coordinates. The representation is like that. The transformation from normalized 3D coordinates to pixel coordinates has to happen now. So you multiply it by k times I comma 0. Then altogether we have this form lambda x, the coordinates in the image. Of course, there's this unknown scaling factor KIO RT01 x. So finally, lambda x equals KRTX, t is equal to minus RC and this is something that we usually remember. Okay. So coordinates of the camera center in the world frame is C tilde. What is the projection of the camera center in the world coordinates? So we can have it like that, and then you will see it's you have 0 here. The camera center is a null, we call it the null space of the projection matrix. So camera parameter summary, intrinsic parameters. So you have in this case, and then principal point coordinates, focal length, and pixel magnification factor. So mx and my. Skew, non-rectangular pixel. So there can be a value here. There can be a value there also, but we will not consider that. And then the radial distortion, this is very important in practice. So if you run camera calibration software, the parameters that are required to correct the radial distortion can be obtained. Extrinsic parameters, rotation and translation related to the world coordinate system. So this is what we studied. Yeah. Okay, let's briefly look at calibration, how to obtain these parameters. Okay, so there are many ways to obtain these parameters. So if you think about the camera calibration matrix, this one, so it's a 3 by 4 matrix. So that means there are 12 parameters, so we need to obtain those 12 parameters. So given endpoints with known 3D coordinates xi and known image projections xi, estimate the camera parameters. So you can use the calibration object like that. We know the coordinates of those white dots. Given endpoints with known 3D coordinates xi and known image projections xi, estimate the camera parameters. So you can see the known 2D image coordinates and the known 3D location. So these you have to estimate, somehow measure and estimate. We have initially fitted the homography like that. We can fit one here. So there are some tricks to be done here to do that, because the parameters are slightly arranged in a more complicated fashion. So lambda xi equals p xi. So what we do is get the cross product with xi. Then on this side you get 0. That 0 is this. Xi cross p xi is 0. When we expand xi as xi yi and 1, and then this as 3 rows in this fashion, and then we can get them into one vector as this. By rearranging, so one mesh gives only 2 linearly independent constraints, because there's linear dependence between these 3 equations. So final linear system would look like this. So we have to have not just one point, but you'll have to have n such matching points. So one 2D 3D correspondence gives 2 linearly independent equations. The projection matrix has 11 degrees of freedom because of that unknown factor. So 6 scaling factor, 6 correspondences needed for minimal solution. So homogeneous is solved by using homogeneous least squares. Find P minimizing AP norm squared. Solution can be found using eigenvector of A transpose A corresponding to the smallest eigenvalue. Using that we can find P. But if all the 3D points are coplanar, that is one single plane, then there exists set of line parameters phi transpose ABCD such that phi transpose X is 0 for all I. Then we will get degenerate solutions. So that is not possible to, it is not possible to estimate P in this case. So there are these linear versus nonlinear camera calibrations. Linear calibration is easy to formulate and solve, but it doesn't directly tell us the camera parameters. So in practice, nonlinear methods are preferred. Write down the objective function in terms of intrinsic and extrinsic parameters as sum of the squared distances between the measured 2D points and the estimated 2D points. So you can estimate the 2D points, right? So that is by projecting in this fashion. So that's the estimated points, and you subtract the real ones, and then you square it and sum it. So that's the error. So this error you minimize by adjusting K, R, and T. Can include radial distortion and concepts such as known focal length, orthogonality, visibility of points, and so on also. So minimizing error using nonlinear optimization package. we can find the K, R and P. Okay. So before moving on, we can look at an example. Okay, so what we do is looking at a point cloud using imaging a point cloud using a camera constructed by specifying extrinsic and intrinsic parameters. Okay, in this case, I have pi file loaded using which I can read a point cloud. So point cloud is a scatter of points, so I will show this point cloud beforehand. So this is the kind of point cloud. You can see these points, they sort of define an aircraft. So you can see that these are concentrated at 0, 0 and 0 of x, y and z. So I have to locate a camera somewhere and make an image. That's what I'm trying to do now. So using this ply file, I can read the point cloud, PCD, ply data read, and then do a little bit of things to obtain the points. Now assume that you have the points here, x, y and z coordinates. And then I concatenate a 1 at the end to make them homogeneous coordinates. Okay, then the first camera I will create like this. So you can see here I have created a rotation matrix. So you can see because it is an identity matrix, there is no rotation. And then K, I decided to use 1 by 1, 1, 1. Actually, I should have put values so that I obtain numbers in pixels, but I decided not to do that. And then T, the translation, I took as minus 4000. And then I created the first camera matrix as P1, K times RT. So that's the formula we had. So this formula. Okay. Then the second camera matrix, I had some rotation. So here you can see my x-axis is now the y-axis. Y-axis is the x-axis and z-axis remains so. So that means a rotation around z, right? Rotation around z. That's what. So look at these rotation matrices on your own and try to understand what they do. And then I have the k also, a little bit of twice the zoom I have given, and then once again you have p2 k times r times t. Then I have to make the two images. First of all, the original the transformed one, p times points, so you just very simple. Of course it is there's a scaling factor, so that we can reduce by dividing by the third coordinate to convert from homogeneous ones to Cartesian coordinates. And then I display the scatter plot, and that's displayed in blue. That's the aircraft. Then I take the second camera. The second camera is actually rotation. There must be a rotation and a zooming because of these two numbers. So you can see I have done the same thing with the second camera also, and then divide by this third coordinate to make them Cartesian and display them. So you can see the with respect to the blue one, second image has been zoomed and rotated. So I took a picture from minus z direction. That's all I did, right? So this is the z direction. I went down in the minus z direction and took a picture. So I think you can see why I got this. Okay, that's that. And then okay, these are the two camera matrices that I have used. Then there is a method to recover a K, R and C given the camera matrix. So for that there is, I have given the code which I found from this place. You have used the so-called archive decomposition in this case. So you can see I have taken the first, so there is an extraction that I had to do. First 3 by 3 matrix, and then some operation that I have to do, and then get the camera center, then using the archive decomposition, K and R, and then so make diagonal of K is positive. It must be done in this case. So that transformation has to multiply R also. Then we can print K and R, so we can see the K and R have been recovered properly. We are doing that to the camera matrix too. Okay, it's good. So in this case, I took the camera matrix even in the Hartley and Zimmermann book. I typed it, it is this exact camera matrix. I want to say P Hartley and Zimmermann. So as you can see, it's a 3 by 4 matrix. I want to recover the K, R, C, K and R from this. So once again, I extract the first 3 by 3 matrix from this, and then this apply this operation to extract C, and then using the RQ decomposition, I extract K and R, and then this diagonal make the diagonal positive, and then these kind of transformations will have to be done. And then I have printed C, K and R. So they are this is C, camera center, K and R. Then once again, by multiplying K, R and C, we can obtain the original camera matrix. That is exactly this. Yeah. Okay.